Very good. So good morning, everyone. Welcome to the ARMA Future Leader webinar. Today, it is my great pleasure to introduce our speaker, Dr. Jennifer Day. She is a geological engineer, and she's registered as a professional engineer and professional geoscientist in Canada. She is an expert in engineering geology, site investigation, physical rock mechanics, rock engineering, geohazards, and advanced computational analysis. Before joining Queen's, Jean spent 3 years as an assistant professor at the University of New Brunswick. She is the first Canadian to receive the Richard Walters Prize from the International Association for Engineering Geology and the Environment. And she is also the first Canadian to receive the Dr. N.G.W. Cook PhD Dissertation Award from ARMA. Currently, she is serving as the past president of the Canadian Rock Mechanics Association and divisions and committees representative of the Canadian Geotechnical Society. And with that, Jean, please go ahead, and the floor is yours.
Thank you very much, Wei. Thank you very much for the invitation, Wei and Bing, for your organization of this webinar series. And thanks to all of you on the call for joining us today. I've had a great opportunity to be involved with ARMA over the years since I first began my research career as a grad student. And so I thought I'd highlight some of where that work has gone. And so today I'll focus on the area of my research on hydrothermal veins and their impact on geomechanics, and look at that from the mineral grain to excavation scales. A lot of this work all of the work in this presentation is work that's been done by myself, as well as my grad students, Matthew Clark, Giselle Rederum, and Emily Gagnon. And it's been an absolute pleasure working with them. And you'll notice, hopefully, throughout the presentation on the different references where they've been involved in different aspects of the work. Matt is now currently working with WSP, and Giselle is working with BGC Engineering, and Emily's continuing work with her PhD. So for the work that you see with her, there's more to come in the next couple of years. So hydrothermal veins, from a geological perspective, are very important in the mining industry, as they host a lot of mineralized zones in porphyry and skarn deposits and similar types of deposits. They have a variety of mineralogies, ranging from geomechanically from very hard, such as quartz and sulfides and anhydrite, through to very soft, looking at more of the epidote micas and into the swelling clays. And the challenge with all of this is, how do we take into account these varieties of geological conditions into geomechanics and for rock engineering design purposes? And so these hydrothermal veins have been found in many cases to have significant multi-scale influences on rock at lab testing scale, and all the way up to rock mass behavior at depth at the excavation scale. You can see an example of laboratory test data on the right from an andesite. The solid lines are the Hoek-Brown strength envelopes for matrix intact rock failure through the matrix, and the dashed lines in this case are failure through the veins. And so you can see there's definite weakening in that strength caused by the veins in this case. And so in my research on this topic, my pitch, I guess, is that veins should be accounted for using an integrative characterization approach for geology and geomechanics. And in this presentation, I'll take you through the different contributions that I've made and my students have made to this story from the excavation scale, or from the mineral grain scale. I'll start small today and go up to the excavation scale. So our story so far with hydrothermal veins is over 10 years, which is kind of tough to believe as I put this presentation together. It began with composite geological strength index, which I'll talk about at the end of this presentation. And that was my first ARMA paper and presentation in Chicago in 2012. And it's gone from there, jumping around in my PhD to looking at numerical modeling of vein microstructure, ARMA 2014, looking at core logging for veined rocks. How do you start to do that scale of data collection? And moving forward, I was able to validate the composite GSI and then expand it, which I'll touch on later. I refined a tool for looking at brittle overbreak and heterogeneous ground. And we've really been focusing lately on the lab sample scale and the mineral grain scale or vein microstructure since then. Matt Clark focused on UCS tests and testing of veined rocks and sample selection from drill core 4 such testing programs. And Giselle Rudderam looked at UCS and TCS numerical modeling of veined rocks and sampling for vein shear strength. And Emily Gagnon continues to build on all of this work, and she's diving further into the vein microstructure. So in this presentation, we'll be in, I think, 5 parts, and it will start small on the mineral grain scale and work up to the excavation scale, touching on all of the progress we've made in these areas so far. So moving right on to part 1, looking at numerical modeling of vein microstructure. And this began where I started thinking about the vein mineralogy, thinking how can we model full width veins? So going from hand samples to cutting thin sections, as you can see on the left side of the screen. First, this began with tracing by hand the grain boundaries, as you can see in the sample image on the bottom left, to represent the actual vein, full width vein material in a UCS model. This is RS2, Rock Science Finite Element software. And then once we have that, can we use input data from literature of mineral grain stiffness and strength properties to then calibrate a UCS sample, and then calibrate really a joint element that could represent the full width of the vein in that single joint element, which is then allows us to upscale to model at the excavation scale, where it's really not feasible to, at the excavation scale, have models with full width veins and have all of the mineralogy reflected in that model. So in this study, the first step was translating those thin sections of rocks to the finite element models. And so there are a few different types. You can see quartz and pyrite veins, number 1. Number 2, there's some embedded wall rock elements, as well as calcite and pyrite elements, gypsum, number 3, and then the muscovite, pyrite, and quartz, number 4. The calibration of the joint elements and the parameters that were used for that are all in the paper, but I don't have time to go through those today. But I will highlight what we observed in the yield progression within the vein material. So looking at that sample number 4 with muscovite, pyrite, and quartz within the vein element in the staged model within RS2, we could see yield happening first in that upper muscovite layer, followed by growth of failure in the muscovite lenses between the pyrite grains, building through to the lower muscovite layer, and then finally some pyrite and quartz grains yielded at the end. In Emily's work, she picked this up at the start of her research career, looking at how do we more accurately leverage structural geology with the vein microstructure, as within the realm of structural geology, and looking at the genesis of how veins are formed. They tend to form in different patterns with different grain sizes depending on their environment of formation. So you can see in some of these thin section images, there are varieties within these calcite veins of the shapes and sizes of these minerals themselves. And so Emily did some wonderful work trying to sort out all of the different structural geology types of veins into this series of 9 sort of vein archetypes. There's 2 main categories of antitaxial veins and syntaxial veins, which you can see noted on the top. Antitaxial veins broadly have a single growth plane or a median zone in the middle of the vein, whereas in the syntaxial veins, you've got multiple growth planes, and the number of them depends on the number of crack seal events that happen through the vein formation. And so Emily went ahead with building finite element models with discrete vein microstructure. So all of the mineral grain boundaries here are joint elements in RS2 models, all with their calibrated input properties, which are available in the paper. And so she looked at what's the effect on the same vein in this UCS sample on the same orientation and thickness, but the only thing that was different was the vein microstructure geometry with these 9 different archetypes. And so the results were quite interesting, and sort of what I expected to see was, yes, indeed, the vein microstructure does have a significant impact on the emergent, in this case, UCS or peak strength properties of the material. And you can see the UCS values for each of the samples in the bottom right corner of each one. But for the purposes of this presentation, we can look at the difference between antitaxial and syntaxial, where in antitaxial veins, the average UCS was significantly lower than in the syntaxial veins. So leaving vein microstructure behind for the moment, and we'll talk next about UCS and triaxial compressive strength, or TCS, laboratory scale insights of veined rocks. And this section involves work from Matt Clark, Giselle Rotherham, and then I'll bring it back to Emily's more recent work on the vein microstructure. So we started for lab testing with Matt Clark's work on the legacy skarn deposit. And this is a copper silver skarn that's Devonian to Ordovician in age, located in northwestern New Brunswick in the eastern coast of Canada. And you can see the cross-section of the deposit on the right side. And we were lucky to work with the government of New Brunswick, their geological survey, to have access to the rock samples from 2 boreholes. And you can see the section of one of the boreholes we looked at is that NBL 1304 that goes through a couple of different lithologies. The UCS testing that Matt did involved 5 lithologies from the legacy skarn deposit. There's 3 varieties of granodiorite: a beige, a red, and a black. And then we've got a calcareous mudstone and the garnet pyroxene skarn. For the veins within these rocks, all of the granodiorites had calcite and anchorite veins that were fairly narrow, about 1 to 2 millimeters. Some of these samples also had some phenocrysts in the matrix. In the calcareous mudstone, this was very fine-grained, bedded, and had calcite veins that were actually varied widely in their width, from 3 to 35 millimeters. And you can see one of the widest veins in that photo on the slide. In the garnet pyroxene skarn, this was a little bit different, where it had a quartz stockwork vein network within the lab sample scale. So all of the other 4 samples, we were able to isolate single inclined veins within our lab testing. But for this garnet pyroxene skarn, we were limited to testing, and it gave us an opportunity to test a vein network, which means we can't just look at a single vein at a time. Another part of the garnet pyroxene skarn units of interest is there are very occasionally large garnet crystals in the matrix, about 3 to 6 millimeters. So when we were doing this lab testing, of course, measuring the stiffness and peak strength, but we also wanted to look at the brittle damage thresholds, so crack initiation and critical damage, CI and CD. And there are a variety of ways to measure these properties, as many of you are probably aware. And these methods were developed for rocks that were more geologically homogeneous, so free of veins, so like the lactobonate granite and other classical examples like that, Indiana limestone, etc. So for these veined rocks, what Matt did was develop sort of a confidence ranking of the quality of data we would tend to get from these different measurement methods for CI and CD for these veined rocks. And when we were then going through and plotting up all of the data, we looked at the variability in what the crack initiation and crack damage results were. So in this case here, looking at the beige, red, and black granodiorites, you've got the matrix only samples and then the samples with veins in them. And you can see there is quite a large variety within that data. For the purposes of this presentation, I've put the means of each of them at the bottom. And so you can see there are differences in the mean CI between the matrix only and the veined rocks. But the really interesting part here is that by layering the confidence rankings of the different measurement techniques, we can then progress to not just relying on a mean value, but we can also start to sort the data a bit more meaningfully to select the more representative CI and CD data points for use in application in numeric modeling inputs, for example. We also looked at characterizing these rock samples geologically, so looking at field identification and those types of observation skills, looked at thin section and petrographic analysis. We also employed X-ray diffraction to look at the crystallographic mineralogy, as well as, the XRD was powdered in a bulk format, and we could separate the sample out between matrix and vein. And then we also looked at a spatial mapping using scanning electron microscope and micro X-ray fluorescence to look at the elemental composition across the thin sections as well. So spatially, we could have a look at some of those characteristics geologically. And I guess the key takeaways from this testing is looking at what's the mineralogy or lithology of the wall rock versus the vein, and how does that vein then impact the strength compared to a matrix only specimen. So in these three examples, we've got red granodiorite on the left. In the top left graph, you can see the axial stress strain data. For the granodiorite, the solid lines are the matrix samples and the dashed lines are the veined samples. And you can see the veined samples are far weaker than the matrix only sample. And then on the middle, this was one of our key insights from this study in the calcareous mudstone. We actually had the veins strengthening the rock, even though calcite is considered to be a relatively soft mineral infill type. For a vein context, it actually provided a lot of strength to this weaker wall rock lithology. And then in the skarn as well, we've got quartz veins, which again are working to strengthen the rock compared to that matrix sample. So you can see here just the UCS peak strength results. There's quite a variety of data points and certainly differences in all of the lithologies between matrix only and veined rocks. So one key outcome from this is that veins were conventionally regarded as defects that weaken rocks. However, our testing does show that it's not only the vein composition, but also the relative strength of the vein compared to the wall rock, where the even softer vein mineralogies can work to strengthen the rock overall. Moving on to Giselle Rutteram's work. And so this was looking at a finite element study of looking at the vein geometry impacts on UCS and TCS testing. This was a study done in the midst of COVID, where we were not allowed to do any laboratory testing. And so we were very grateful to be able to find lab testing data in the literature to facilitate a lot of this research, and particularly the thesis by Mr. De Los Santos Valderrama from Chile. And so these rocks are from the El Teniente mine. In this study, Giselle looked at modeling vein orientation of 5 to 85 degrees in 5-degree increments with respect to the core axis, and looked at vein thicknesses of 1, 4, and 8 millimeters. In this study, it involved rigorous multi-stage modeling calibration of non-veined rocks and then veined rocks. And we used this lab test data available in the literature on the sulfide veined cement rocks from El Teniente to validate these models and carry out our analysis. And so the multi-stage model calibration and validation first involved using well-published and well-understood lactobonate granite to simulate the UCS and TCS tests. And this rock type was used to calibrate the model settings, so the mesh, staging, and platinum specimen contact properties. Then using that model setup, Giselle simulated unveined UCS models of the cement rock, and then used the lab test data to calibrate that. Then added the vein to that model, and then also did use published TCS data to validate the model against for the veined cement sample. So here's an example. Here's all of the 10 MPa confining stress rock types organized by vein orientation and vein thickness. And these are RS2 models, again, finite element. And you can see as you go from the left side of this where you've got a low angle, so near a subvertical vein, and then it starts as type A failure, through the vein and the contact. And then as you increase that angle of orientation toward horizontal, you get more failure through the vein and wall rock, and then through the wall rock alone, and the vein is less and less involved with that. The couple of insights from this data is the lowest, this is again the 10 MPa confining stress. The lowest peak strengths in this were between vein orientations of 20 degrees and 40 degrees. The thicker veins tended to be weaker when they were oriented subvertically in the lower angles, and stronger in subhorizontal veins. So we had that mode switch, which was an interesting observation that we weren't necessarily expecting. Looking at the influence of confinement, when you think about TRAXIAL tests going from 0 MPa confinement for UCS tests through to 5, 10, and 15 MPa, generally in this experiment, the higher confinement increased peak strength for all vein orientations, as you would expect, but it also produced greater variability with different vein orientations. So the amount of increase in peak strength was much higher at vein orientations of less than 30 degrees and more than 60 degrees. Another useful result from this work is we were able to provide some guidance for UCS or TCS lab testing programs for rocks that are similar to the CMAT with sulfide veins. So if you're wanting to measure the shear strength of sulfide veins with TRAXIAL tests, this data suggests that it would be good to include samples with single vein orientations distributed throughout the 5 to 50 degree range. You can see in the normal stress versus shear stress plot below, where the alpha is the angle of the vein orientation. Each vein orientation would give you a smaller section piece of that failure envelope. And so by combining them with multiple orientations, you would get data across along a wider amount of normal stress range. There is a slight statistical preference based on the confidence interval curves to use a lower lower confining stress, between 0 to 5 MPa, as opposed to necessarily saying you need a full distribution from 0 to 15 confinement. So this, as an output of this study, we recommend to test a minimum of 8 TRAXIAL specimens per wall rock lithology and vein mineralogy, and categorize your observed failure mechanisms, such as through the vein or through the wall rock contact, to help you sort the data and calculate the shear strength envelope. Now, if you're looking at rocks with stockwork networks of veins, you do need to be a bit more careful. You may not be looking at being able to use the shear strength of the single vein for discrete vein elements in your model, but you may need to rely on the tests of stockwork samples to determine your intact rock properties, such as through the Hook-Brown criterion or similar. So coming back to Emily Gagnon's more recent work, carrying on with this theme of diving into vein microstructure and looking at the variability by vein orientation. So building on Giselle's. And Emily looked at these 4 types of vein microstructures, but I'll just show you the results for the 2 anisotropic elongate blocky and the polycrystal bridged. For the polycrystal bridged, you can see that there is variability in that UCS peak strength with that variable vein angle. And what's important to note in this work is we're not just looking at the vein angle from 0 degrees to 90 degrees, so vertical to horizontal, but because now that there is an isotropy within the vein itself, we have to model all the way around to capture 0 through 90 and all the way down to 180 to see the different orientation of the vein relative to the core axis itself. So there is some slight differences as you go around when the vein is sort of inclined one way and then when it's past that horizontal point. So in the polycrystal bridge type of vein microstructure, there is a 20 to 45% strength reduction from the wall rock only specimen with no vein. In the anisotropic elongate blocky, there was a 15 to 69% strength reduction. In the other 2 cases, which are available in the paper, there was even more strength reduction observed, but I'll leave that for you to go find afterwards. And one other note is that Emily sorted these failures by if the sample failed through the vein, infill, the vein wall rock boundary, or a combination failure involving the whole sample with the wall rock, including spalling, axial splitting, and explosive. Here are some examples of what these failure modes look like in the RS2 models. So on the left, we've got the vein failure infill, looking at volumetric plastic strain, the vein failure through the vein wall rock boundary, and you can see that from the shear, failure in the material and near that boundary as well. The combination failure of the vein and the matrix, spalling, as on the right, there's a combination failure of more of an explosive failure where you can see a very rapid change in volumetric plastic strain in the stage immediately before failure versus at failure. So moving on from our vein microstructure and moving into drill core logging and sample selection. So this early work that I did as part of my PhD looked at developing new geotechnical core logging techniques for incorporating veins with different amounts of detail and to try to figure out how much detail do we really need in order to input the drill core data into numerical models for excavation scale modeling. And method 1 is sort of your basic drill run data, RQD, Q prime, RMR. Method 2, which was at that time sort of the state of practice in industry, it incorporated looking at joint surface information such as roughness, alteration, Barton-Bandis and infilling properties, and then also the lithology as well. For method 2B, this is where I introduced a very basic assessment of the block size or spacing of veins or intrablock structure. Veins are a type of intrablock structure, and the type or mineralogy. And then in method 3 and 4 of the core logging, really method 4, I looked at adding more information about the thickness of the veins, alteration, loose hardness, and then orientation as well for oriented core. And so from the most rigorous type, the method 4B, where you've got orientation data and spacing data from the drill core, you can start to get that information, which would enable you to use that as input for discrete fracture networks or other discrete modeling of vein elements. And so you can see, similar to joints and other fractures, you can have varieties of spacing. In this case, this is in northern Chile. These rocks, there's a bimodal distribution of vein spacing from less than 10 centimeters to 20 to 60 centimeters. And then also in the vein orientations, you have 2 or more sets, as well, similar to what you would find in joints. So very valuable information that can be gained from logging veins and drill core. And so for the implications, I recorded the logging times it would take to actually collect all of this data. And so these are all normalized to that unoriented conventional method 1. And looking at unoriented to oriented core, as you'd expect, the time increases quite dramatically. And so if you're going from conventional QRMR, ignoring veins entirely, just looking at joints, that's the time of 1. If you then go into adding detailed vein information, so the type, the spacing, that doesn't really add too much time to it, double the time. And then when you get into the oriented core, you really do get into quite a lot. So the takeaway from this is you get significant information added to the core logs for basic but valuable considerations of veins. And if you are working in a project where it is really important to understand the orientation of the veins, this study does give you some framework to how to approach that and incorporate it into your core logging activities. So from drill core, of course, that's where we often select samples of rocks for UCS testing. And in Matt Clark's work, when he was looking at selecting his samples from the Legacy Skarn deposit, we determined that there were, at that time, no universal sample selection standards for UCS testing. The ISRM guidelines recommend to not test rock with defects or veins, which was not very helpful because we wanted to test rocks with veins. So we asked some colleagues for their professional experience. So 4 practitioners, they said that they work with their own judgment and company guidelines. Often there's an agreement with the client on the number of tests required, where a certain number of samples are selected from each geotechnical domain. And sometimes the samples are selected at predefined intervals. In general, these 4 practitioners considered the following main factors when making sample selection decisions. What stage of the project are you at, from scoping, pre-feasibility through to operation? What geological setting are you in? What's the variability of the rock mass? What existing material characterization exists in the database? What is the project risk and uncertainty? Are you looking at a mine, or are you looking at a nuclear waste repository, for example, or anything in between? What's your project budget as well? And so in Matt's work, we wanted to provide some new guidelines for what's a good practice to consider for selecting samples in veined rock masses. And so in this, this is the Legacy deposit. This is one of the boreholes that Matt looked at. And I'll just walk through the different lithologies that are here. You can see the samples that were selected from the core are highlighted with the white rectangles and yellow. Some of them failed during preparation, unfortunately, but that does happen sometimes. So in this deposit, in this borehole, rather, we have calcareous mudstone, which is the dominant part of it. We've got the beige granodiorite, the red granodiorite, and the black granodiorite. And I'll take you through the different sample selection methods we looked at in this analysis just for the calcareous mudstone. So focus on that blue section of rock. The 4 different sample selection methods we tested, we're saying what's standard practice to look at homogeneous samples only without any veins, looking at heterogeneous samples only, so only ones with veins, all of the samples we could possibly get with a combination of matrix only and veins, veined samples, and then the fourth one is an objective sampling within each lithology at a minimum of a 2-meter interval. So out of all of the samples we collected and tested, we could then go back and reanalyze the data by sorting the data based on these different sampling methods. And so for method 1, the samples that are without any veins are circled in red. So out of all of those calcareous mudstone samples, these are the 6 that went into this data set. If we were to only sample the rocks with the veins, there's those 4 samples in red. Samples selected for method 3 are all of them, and then an objective sampling 2-meter interval, minimum 2-meter interval, is this method 4. And so here are the results by sample selection method for all of the different lithologies in this study. If you focus just on the left on the calcareous mudstone, you can see there's a pretty significant difference between, method 1 if you're ignoring the veins entirely versus method 2 where you're only doing veins, and then even that method 3 and 4 as well. So the objective sampling 2-meter interval method is what we'd recommend, as it does give you that inclusion of both matrix type and vein samples. All right, so moving right up to the excavation scale, looking at first a field assessment of brittle overbreak in geologically heterogeneous ground. And this is work that I was lucky enough to do at El Teniente during my PhD thesis. This work builds on this empirical tool for looking at brittle overbreak in homogeneous ground that Derek Martin, Mark Diedrichs, and I think Peter Kaiser was also involved with. And this empirical data set with the linear function was drawn from a variety of lithologies, but most of them were fairly homogeneous, such as the Lactabanet granite. When I plotted the data, so in El Teniente, when we went into this case study, we had 3 different lithology groupings. We had the stockwork-mafic complex, dacite porphyry, and a couple of breccias. With field observations and overbreak data combined with having some database of laboratory testing, I was able to plot what the overbreak would be on that graph. And it really, the data sets did not agree with that original linear function, which you can see in this graph in that dashed line. So to address that, I looked at adopting some excavation damage zone depth functions from work by Matt Perra to have a general form for looking at being able to pick your own coefficients that capture the data for these heterogeneous ground. So in the stockwork-mafic complex, we have a lot of very persistent planar veins. And in the brittle overbreak observations at depth, we found there was a sort of extended spalling, very high overbreak and vein interaction, which resulted in overbreak above what would be expected with the homogeneous ground function. The dacite porphyry exhibited fairly classic spalling. There was not much going on for geological heterogeneity, and there was sort of that notch stabilization, which aligned a bit better with that linear function. And then in the brecciated units, there was actually a lot less overbreak than what would be predicted by that homogeneous function, ground function. And we interpreted this as the breccia class themselves ended up resulting in terminating cracks of spalling. And so the spalling was incomplete and not able to form and further develop. So this really allows you to, these observations show that the different geological heterogeneities, whether you have different types of veins or breccias, can either enhance or inhibit fracture propagation at the excavation scale. That would create much larger variability in brittle overbreak. And so the general form of the equation for that I proposed allows practitioners to use their own data for lab testing and overbreak observations in their own excavations and geologies to use that function to start to be able to predict what brittle overbreak they may expect at different stress conditions. All right, and the last part of this presentation is, again, at the excavation scale, looking at field characterization of veined rock masses. And so this is the Composite Geological Strength Index work that started way back. ARMA 2012 was its sort of when it was born. And so this composite GSI is an expansion of Cook's and Marinos's Geological Strength Index to incorporate intrablock structures such as veins into continuum numerical models via direct input to the Hook-Brown shear strength criterion. In the GSI chart itself, for the composite GSI chart, there's an additional column, which is highlighted in yellow, which allows for strengthening intrablock structures, such as those quartz veins and sulfide veins. And there's other descriptors in the infill and surface conditions along that top part of the chart that adds some information about types of veins. There's new equations for the composite GSI, which is really the magic behind it, where you start with evaluating different sets or suites of structures individually, such as just look at the joints and just look at the veins, and then through these formulas, put them together into that more holistic CGSI number for input into numerical models. And so there's a couple different ways you can use CGSI. Again, that philosophy is that you first consider your structures individually and then combine them for a single rock mass value. There's two approaches. The first one is by looking at block volumes of structural suites. And the second approach is by spacing of structural sets. There's more detail on this. That's in the conference presentation I gave for the Rock Science International Conference, which is on YouTube at that link if you're interested, as well as the some case examples of how these two approaches work are presented in that paper. So overall, key conclusions from this area of my research so far is that we can understand variability in emergent UCS and TCS test results by analyzing vein microstructure, mineralogy, orientation, and thickness, plus the wall rock lithology. We can capture variability by selecting core samples for UCS and TCS testing that contain a variety of matrix-only and veined rocks and vein orientations for all lithologies and vein mineralogies. We can design laboratory test programs of veined rocks to capture relevant data for equivalent continuum or discontinuum models based on rock engineering design plans. And we can and we should leverage the geological data that's available, including structural geology, lithological alteration, and others, to enhance our geotechnical data in a project. We can improve tunnel design and construction by using customized empirical overbreak functions for heterogeneous rock masses, whether they're veins or breccias or other geological heterogeneities, with that general form function for brittle overbreak. And lastly, we can characterize multi-component rock masses in the field using the composite GSI tool for direct input to numerical models via the Hook-Brown shear strength criterion. So thanks again. I'd like to highlight my team's work in all of this research to date. So Emily Gagnon, Giselle Rederin, and Matt Clark. And for further interest, here are some related publications to all of the work in this talk, sorted by the vein microstructure scale. looking at UCS laboratory testing, physical testing and numerical modeling of those, looking at the drill core logging scale and sample selection processes and the excavation scale contributions as well for brittle overbreak and composite GSI. So lastly, I'd like to thank all of the funders and collaborators for this research, which was certainly a pleasure to work with all of these fine people, and very grateful to have access to some of the data and field sites that I've been able to. So thank you very much for your attention, and I'd be happy to answer any questions.
All right, thank you, Jane, for a very comprehensive lecture from grain scale all the way to field scale. So let's see if we have any questions from the audience. All right, I see Shazad side. Thank you, Jennifer, for the great presentation. I must get to another meeting, but I'll follow up with you about some questions later. Yeah. And would you like to turn on your mic, or I can read it as well? Well, I guess the first one from Ed is more of a comment. It seems that in cases where core is quite variable, such as what you showed in the UCS sampling exercise, continuous measurements along the core, such as crash for high-resolution UCS, could be of value. Dual energy CT scans can also be used to provide a 3D digital record of vein locations and orientations. Jane, would you like to add on
Ed,
that?
I think you're spot on with that. Having that continuous logging approach with the CT scanning, or even the hyperspectral scanning as well. That's certainly that would add value to core logging and be able to capture some of this variability, be able to categorize and identify different veins. If you are doing any of this type of core logging with CT scanning or hyperspectral, I'd love to chat with you to build on some of this work.
Okay, the next one was from Mike. By the way, very nice modeling. Did you say that that was done with Rockfield FEM software?
Yes, it was done with the Rock Science finite element software, the RS2. Well, RS2 now, but the original 2014 was phase 2 back in the day, I guess.
The comment from Carlos. Thank you, Dr. Day. Time to take this to practice.
Thanks very much, Carlos.
So if any one of you has questions, feel free to turn on your mic or type in the chat and I'll read it to the audience. I see Wencheng turned on the camera. Wencheng, do you want to start?
Yes, thanks, Dr. And thanks, Dr. Day. That's a very nice presentation and excellent work. So I have two comments and sort of questions as well. So the first one is about your simulation. Looks like all of them are 2D simulations, is that right? So if it's 2D and also your data is coming from the 3D, do you think that there will be some inconsistency or how this can be corrected? So that's my first question and comment. And the second one is, nowadays, especially in US and also in Canada, I think we are really, from the government side, also from the society side, we need lots of critical minerals, and all these critical minerals are actually residing in these veins. These veins have lots of this type of minerals. So I was wondering, from your perspective and also your study, how your study can be contributed to mining those minerals from these veins. Thank you.
Thanks for your excellent questions. I think your first one was asking about in our models. They are 2D, the ones that I've shown here, for the UCS and TCS testing. And yes, certainly there are considerations to be made to compare 2D models to 3D models. In Giselle's work in particular, they're in her model calibration process. In the paper, there's discussion about how she converted the 2D and to 3D to 2D, Young's modulus and Poisson's ratio in particular, for calibrating those results from the lab testing. So I'll be happy to send you a copy of the paper if you have trouble finding it, for more details about that. And then for more recent work, I know Emily's working on some more 3D modeling to capture that as well. So stay tuned on that to come. For your second question, certainly a lot of the critical minerals in Canada is a hot topic, and I hope this work is very helpful for practitioners in that space. And certainly the point I made for geotechnical engineers or rock engineers to incorporate geological data, I think becomes simply more and more important to take advantage of the data that in many cases is already being collected by geologists that we can use to understand geomechanical variability or trends. And also in a project, I would envision the ability to use some amount of laboratory testing for UCS Traxial, that kind of suite, and then be able to expand and extrapolate those results to other areas of the rock mass based on input from the structural geology and other geological and other geotechnical core logging.
Thank you so much for answering. Yes, I would love to. I will check your papers, and if I couldn't find the papers, I will reach out to you. Thank you.
Thank you.
Thank you, Wencheng. Anyone has other questions?
I had one, if anyone else didn't want to jump in before. You showed one slide where you, in the model, where you changed the angle of the vein and then you saw explosive failure. But it seemed like from the slide that there was only one orientation where it happened. I was wondering if you comment on if that specific configuration just behaved so differently that you felt that that was the case, or was it sort of a transitional sort of thing?
I think in some of the other vein microstructure types that I did not cover in this talk, that explosive failure was also there. So it wasn't only in that one case where it happened, but the animated piece of it that was part of this presentation, the dramatic difference from the stage before failure, having absolutely no yield going on, to right after failure, pretty much everything was a significant enough difference to classify it differently compared to the spalling or axial splitting failures.
Okay. Did you have if you looked at the axial or volumetric stress strain curve, would that be very different then in terms of its peak behavior?
You know what, Bing, I'd have to direct you to Emily for that very specific question.
Okay.
Maybe if you send me an email afterward, I'm sure we'd be happy to follow up with you on that.
Okay, cool. Thank you.
Thank you.
Okay, I actually also have a question if anyone is not asking questions. So for your grain scale modeling, so have you observed any mesh size dependency because you're looking at macrostructural behaviors? And also, how would you quantify the intergranular and intergranular behaviors if you are using an FEM approach?
Sorry, was your first question about mesh?
Mesh size dependency. For example, if you are really looking into these microstructural behaviors, how would your mesh size influence the actual simulation results?
Yeah, certainly. In the work that Giselle was doing to calibrate the mesh, that was mesh on the scale of the UCS test, and so there was some exploration done on that mesh dependency. And as you may expect, at that scale and the amount of mesh size you'd be testing, there wasn't too much of a difference in the emergent UCS properties. But I do know that in Emily's microstructure work, she did spend some time thinking about what that mesh size should be, and certainly making sure that there aren't any sort of bad mesh elements, having a regular triangular geometry of that and having a sufficient number of mesh triangles between the I guess, joint element boundaries between the mineral grains was part of that work. And I do apologize, I can't speak to more of the specific results of that, but it certainly is a normal part of our modeling technique.
Yes, my second question was more about, like, have you considered using a discontinuum approach to look at this grain scale behaviors, intergrains or grains and vein interaction behaviors?
Yes, that
Vein
is
boundary.
in progress way. Yep. Check back soon. More to come.
Cool, great. All right. Well, thank you very much for the wonderful presentation. It's very interesting, very comprehensive, and I look forward to your new research in the coming weeks or months. And
Thank you very much,
again.
Wei. It was a pleasure, and thank you all for attending.